Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So, today we're going to be talking about section 3.5, where we will be looking at non-homogeneous equations and undetermined coefficients. Undetermined coefficients. Alright, so the idea is we already know how to find, So the idea is we already know how to find the complementary solution for constant coefficient differential equations, but what about the particular solution? So the idea is we want a method to get yp. So the method that we're going to use is what's called the method of undetermined coefficients. And here's the basic idea. So the way this works is start first by finding the complementary solution. So find yc, the complementary solution, which you will recall is the solution to the associated homogeneous equation. And you recall that what makes an equation homogeneous or not is the term that does not include the y, whether so it's the what we call f of x, and it is going to be 0 if it's homogeneous or otherwise not. So find that first. Then look at f of x and list the functions that could be the result of differentiating f of x up to the order of the differential equation. So what that means is if it's like an x squared, then you should include such things as the 0th derivative, first derivative, second derivative. So you should have such things as constant terms and possibly just x's, and then x squareds as well. All right. Then so look at the list of the functions and give each a coefficient to be solved for. Then, if there are any from the list that duplicate terms from YC, multiply by enough x's to disambiguate them. You'll see this best in an example. Then take the derivatives suggested by the left side of the differential equation and create the combination you get from plugging your functions in for y, then this should enable you to solve for the missing coefficients. Attempt to solve for the unknown coefficients. By collecting and equating like terms. Alright, so enough strategizing. Let's actually just try this. So the thing about any kind of a description is you never know what's really at stake until you give it a shot. So here's an example. Constant coefficient, and it's going to look like this. Y double prime minus y prime minus 6y equals x plus 1. So this is what is the f of x. Okay, well, first off, what we're going to need to do over here is set up the characteristic equation to find the corresponding values for the r, and then that'll give us the complementary solution. So this corresponds with the characteristic equation r squared minus r minus 6 equals 0, which we can factor into r minus 3 times r plus 2 equals 0. So r equals 3, and r equals negative 2. Setting each of those in turn equal to 0 would give us that. And that gives us a complementary solution of c1 e to the 3x plus c2 e to the negative 2x. So we needed this purely in order to find the pieces that we'd need to make sure that our terms over here didn't coincide with. Okay. Now here we look at the derivatives of f and the various things that can come from it. F being a polynomial, basically what we're just going to look for is terms of degree this and less, because of the fact that we're going to have second derivative, first derivative, and zeroth derivative of y all in play. So we're going to have things along the lines of ax and b. So this is our list of candidates. So that gives us yp is equal to ax plus b. Alright, let's just stop there. So these are the sorts. So this is the sort of thing whose derivatives you get from f of x here. All right. So then, if we were to look at this as a potential, and you look at that and make sure there's no ambiguity between the terms there, nothing stepping on the toes of any terms over there. So here, then what you would do is you would take yp prime would just be equal to a, and yp double prime would be equal to 0. So then we would take this, and this, and plug them into that, and hope that we can solve for the a and the b. So yp double prime minus yp prime minus 6yp equals x plus 1. So that's going to be 0 minus a minus 6 times ax plus b is equal to x plus 1. And so collecting all the like terms and whatnot, we're going to have negative 6ax, and then we're going to have minus a minus 6b equals x plus 1. So then for constant terms and for x terms, we can collect those. Or alternatively, if you think about it the same way we thought about it before, you can just think of it as setting x equal to 0 and doing like that. But in any case, so the x terms are going to give us negative 6a equals x, which means that negative 6a equals 1. And so what that means is that a equals negative 1/6. And then from the constant terms, what we have is negative a minus 6b equals 1. This is, by the way, also what you get if you just think of it as plugging in 0 for x. But in this case, if a is known to us to be negative 1/6, then that means negative a would be positive 1/6 minus 6b plus 1. So negative 6b is equal to 5/6. And so b is equal to negative 5/36. So then that's going to give me a particular solution of yp is equal to negative 1/6 x minus 5/36. Which gives me then a general solution of y is equal to c1 e to the 3x plus c2 e to the negative 2x minus 1/6 x minus 5/36. And it would be initial conditions that we would use to solve for the C1 and the C2. Alright, let's try this again. This time with something that's a little bit closer to the requirement of needing to disambiguate. Still not quite though. So let's take y double prime minus y prime minus 20y is equal to e to the 2x. So now, again, to find the yc, we would need to set up the characteristic equation. So r squared minus r minus 20 equals 0. Which then factors to r minus 5 times r plus 4 equals 0, which gives you an r equals 5, and an r equals negative 4, which gives you a complementary solution of yc equals c1 e to the 5x plus c2 e to the negative 4x. Now, as for an expression like this, if f of x is equal to e to the 2x, then all of the derivatives of f of x are going to also have that exact same form. So then the candidates that we get are e to the 2x, which means yp is just going to equal, and I guess put in a coefficient a. So yp is going to equal just a e to the 2x. Now, if this matched either of these, then we would need to put in enough x's to clear it. So it would have to be different from those ones. But because it's still the same, we don't have to worry about it. So then y prime of p is going to be 2a e to the 2x. And yp double prime is going to be 4a e to the 2x. And if we put these all in play here, we should be able to solve for the a. So yp double prime minus yp prime minus 20yp equals e to the 2x. So that means that we're going to have 4a e to the 2x minus 2a e to the 2x minus 20 a e to the 2x equals e to the 2x. Combine the like terms and it looks like negative 20a minus 2a plus 4a is going to be a total of negative 18a e to the 2x is equal to e to the 2x, which means then that negative 18a equals 1, or, in other words, a equals negative 1/18th. So, what that means then is that our overall form of the general solution for y is going to be a combination of the complementary solution c1 e to the 5x plus c2 e to the negative 4x, but then also, so this means yp is going to equal negative 1/18th e to the 2x, but then there's also going to be minus 1/18th e to the 2x. Alright, let's try another example, this time one that involves some trigonometric functions. So, as another example, let's go y double prime minus y prime minus 12y is equal to sine 3x. So first, we need to find the complementary solution, so we need to set up the characteristic equation r squared minus r minus 12 equals 0, which we can factor to r minus 4 times r plus 3 equals 0, which gives us r equals 4 and negative 3, which means that our complementary solution, y complement, is equal to c1 e to the 4x plus c2 e to the negative 3x. Alright, now, as for the f of x here, this is equal to sine 3x. So we look over the roster of all the derivatives, from the 0th derivative to the first derivative to the second derivative, and the sorts of things that we encounter in so doing are things like this. We have things of the form a sine 3x. We have things like b cosine 3x. Now, as we take derivatives and such, the 3's would come out, but those can just get absorbed by the coefficients, and so it's not a big deal. And that gives us then a particular solution of a sine 3x plus b cosine 3x, which we then need to take the derivative and then the second derivative of this in order to get our way to something we can plug into here. So we take the derivative of this and we're going to have 3a cosine 3x. We're going to have here minus 3b sine 3x. Then when we take the second derivative, we're going to have here, the derivative of cosine is negative sine, so it's going to be negative 9a sine 3x. Here the derivative of sine is positive cosine, so that means we're going to have negative 9b cosine 3x. Alright, so now when we proceed, we are going to need to put all of these into play. So negative 9a sine 3x, so negative 9a sine 3x minus 9b cosine 3x That's going to be y double prime minus y prime. 3a cosine 3x minus 3b sine 3x. That's y prime. And then minus 12 times y, so it's 12a sine 3x plus b cosine 3x. And that all equals sine 3x. Now combining like terms and whatnot, we are going to end up with, let's take the cosine 3x first. So we'll just figure out everything that goes with the cosine 3x. So we're going to have negative 9b. We're going to have minus 3a. We're going to have over here negative 12b. And then for the sine 3x, we're going to have over here minus 9a. We're going to have from right here minus 3 plus 3b. And then over here we're going to have minus 12a is equal to sine 3x. Okay, so then we can combine some of the terms. So cosine 3x times, collect the b's, and it's going to be minus 21b minus 3a and then for the sine 3x we are going to have here minus 21a plus 3b. That all equals sine 3x. Now collect the like terms from each side. So cosine 3x. On the left side, it's going to be negative 21b minus 3a. And on the right-hand side, it's going to be 0. So simplifying this a little bit, we can pull out a negative 3, so that's going to be 7b minus or plus a equals 0. Sine 3x, so the terms that correspond with that, we're going to have negative 21a plus 3b equals 1. So thinking about this over here, a equals negative 7b, which we can then put in over here. Negative 21 times negative 7b plus 3b equals 1. And so here we have 21 times 7. So that's 41 or 49 times 3. So that would be 147? Yeah, 147b plus 3b equals 1. So b equals 1/150th. Which then means a would be negative 7/150ths from right there. Which means then that the particular solution would be negative 7/150ths sine 3x plus 1/150th cosine 3x, which gives us then a general solution y equals c1 e to the 4x plus c2 e to the negative 3x minus 7 over 150 sine 3x plus 1 over 150 cosine 3x. Okay. Now, let's have a look at what happens when there is an overlap between the complementary and the particular solutions and how we deal with that. So, here's an example of one where this will happen. So we'll have y double prime minus y is equal to e to the x. So here we have r squared minus 1 equals 0, which gives us r equals plus minus 1, which gives us a complementary solution of c1 e to the negative x plus c2 e to the x. And it doesn't matter which of the c's goes with which of the r's. Now, as for the particular solution, we note that since f of x is equal to e to the x, the derivatives of this up through the second derivative are all going to be the same. So we would like on our list of possible derivatives, we'd like e to the x. However, that's already spoken for. So there's already a duplicate there, so no good. So then what we do is we put an x in front. And we hope that that's going to be enough, so that it doesn't step on the toes of what we had. So then the particular solution is ax e to the x. Now here, we're going to need the second derivative, so we got to take the derivative and then again the derivative. So we take the derivative, it's going to be a product, so we use the product rule, and that's going to be e to the x, and then plus ax e to the x. So that'll be the first derivative, and then the second derivative will be the derivative of that, so that's going to be a e to the x plus a e to the x plus a x e to the x, which will be 2a e to the x plus a x e to the x. So then, y particular double prime minus y particular is supposed to equal e to the x. So that means 2a e to the x plus ax e to the x minus ax e to the x is supposed to come out equaling e to the x. Notice those cancel, and what we get is 2a e to the x equals e to the x, which means that 2a equals 1, which means that a equals 1/2, which means in turn that the particular solution is going to be 1/2 x e to the x, which gives us then as our general solution y is equal to the complementary solution c1 e to the negative x plus c2 e to the x plus the particular solution 1/2 x e to the x. So again, the way we dealt with duplication is add x. So we couldn't have e to the x, so we had to have x e to the x. But the duplication may be worse than that, and when it is worse than that, it becomes a little bit more complicated than that to deal with. So let's have a look at what that can look like. So let's take as our next example something like this. So we'll say the third derivative of y minus the second derivative of y is equal to 3e to the x minus x squared. Alright, so over here, r cubed minus r squared equals 0 would be the characteristic equation, which means r squared times r minus 1 would be what we would have over here, which means r equals 0 with multiplicity 2, and r equals 1. So this is going to give you e to the x. This is going to give you e to the 0x and x e to the 0x. Again, we avoid duplication by throwing in an x. So this is just going to be 1x and e to the x for our pieces, which means our complementary solution is going to be c1 plus c2x plus c3 e to the x. Now, over here, f of x equals 3e to the x minus x squared. So from this part, we would want to have e to the x as a good candidate for a term. However, it's duplicated. So we need to make it x e to the x. So that would then do it. Now from this one, we would want x squareds, x's, and 1's. However, this and this are both being, those are both being duplicated. So what that means is I have to multiply by a big enough x here to clear that one. So I can multiply this by times x squared, and times x squared. So this is to avoid duplication from YC, from the complementary solution. So these would have stepped on the toes of the first two there. So I have to multiply basically all of these by a sufficient power of x to clear them all. So that's going to give us like a x to the fourth. No, sorry, I already used a. So I should say now like b x to the fourth, c x to the third, and d x squared. So then that gives me a form of the particular solution of ax e to the x plus bx to the fourth plus c x to the third plus dx squared. And again, I would have wanted this to have just been constants, x's, and x squareds. However, constants and x's were already duplicated over here, so I had to up the ante a little bit on this one. Alright, well, then what that means is that for my yp prime, I'm going to have to take the derivative, and here again the product rule, a e to the x plus ax e to the x. Here I'm going to have 4bx cubed, 3c x squared, plus 2dx, and then y particular double prime is going to be a e to the x plus a e to the x plus ax e to the x plus 12bx squared plus 6cx plus 2d, and then I can combine like terms a little bit and get 2a e to the x plus ax e to the x plus 12bx squared plus 6cx plus 2d. Alright, and then I put these. Looks like I need to keep going here because I need the third derivative. Oops, so yp third derivative. Well, I've already taken the derivative of this before. I already know how it's going to go. So cut to the, no, I won't cut to the chase. So 2a e to the x plus a e to the x plus ax e to the x plus 24bx plus 6c, and that one will be gone now. Alright, now what I need is the third derivative minus the second derivative to equal what we were given. So yp third derivative minus yp double prime should equal 3e to the x minus x squared. And it's going to take the right values of a, b, c, and d to make this happen. So let's have a look. What we have here is 2a e to the x plus a e to the x plus ax e to the x plus 24bx plus 6c. That all minus the second derivative, 2a e to the x plus ax e to the x plus 12bx squared plus 6cx plus 2d. That's all equal to 3e to the x minus x squared. Alright, well, let's notice here the negative is gonna distribute in. So I should have combined those like terms, but it's alright the way it is. It's fine because now those just cancel each other out, and that will be nice. And furthermore, those cancel each other out, and all that's left is that one that survives. On this side of things, we don't have anything that cancels, but we do have some like terms. So let's see what we've got here. A e to the x, and then for the x squared term, plus x squared times negative 12b is the only x squared term, plus x times 24b plus 6c plus, on the constant side of things, 6c plus 2d is equal to 3e to the x minus x squared. So here That's the first piece. This is the second piece. These are the third piece. And now that I see this should be a negative, so correct that. And then these would be the fourth piece. And by the same token, that should also be a negative. So be careful about that. It was a negative in front of that the whole time, just lurking out there, waiting to pounce. Negative and negative. Okay. Now, if we put the pieces together here, so the e to the x terms, we're gonna get quickly some resolution there. A equals 3. From the x squared terms, we're gonna quickly get some resolution there as well. We're going to get negative 12b equals negative 1, which means b equals 1/12. From the x terms, we're going to get 24b minus 6c equals 0. Pull out the 6, and that's going to give 4b minus c equals 0. So c equals 4b will probably be useful. Indeed, because that gives us over here that c equals 4/12, or in other words, 1/3. And then from the constant terms, 6c minus 2d equals 0, which means then 3c minus d equals 0, so then 3c equals d, which means, d equals 1 from that. So that then gives us our pieces of the complementary solution. So then the complementary solution is going to be 3 for a, so 3x e to the x plus 1/12 as the b was the x to the fourth term, so that's going to be 1/12 x to the fourth plus 1/3, and then c here represented the x cubed term, plus 1 times x squared. And so that gives us as a general solution c1 plus c2x plus c3 e to the x plus 3x e to the x plus 1/12 x to the fourth plus 1/3 x cubed plus x squared. And now just a note, initial value problems. So IVPs you would use, so you use initial conditions to find the values of C1, C2, etc. in the complementary solution in YC. After finding the general solution y equals yc plus yp just as above. But the technique for finding the using the initial conditions to find the constants of the complementary solution is not substantially different from what it was in the previous sections. So, on that note, let's call it a section, and I'll see you next episode of Math 256. Bye.